Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
Well, a very good afternoon and welcome. My name is Chris Bishop. I'm the Director of Microsoft Research in Cambridge. Great pleasure to welcome you to the Microsoft Distinguished Research Lecture. And an especially warm welcome to the visitors, and particularly if it's your first visit to Microsoft Research. So it's a great pleasure today to welcome Sir Timothy Gowers as our lecturer. Timothy, of course, is a very noted British mathematician. He's a Fellow of the Royal Society. He holds the Rouse Ball Chair of Mathematics at Cambridge. He's also a Royal Society Research Professor in the Department of Pure Mathematics and Mathematical Statistics, and he's a Fellow of Trinity College. He's worked on Banach spaces, Ramsey theory and random graphs and random sets, and a problem that's familiar to many of us, the problem of P versus NP. In 1998, he received the Fields Medal, which I think is widely agreed to be the highest honour that a mathematician can receive, often compared to the Nobel Prize, and that was for research connecting the fields of functional analysis and combinatorics. Now, as well as doing his deep research, he's also very interested in communicating mathematics to a broader audience. Many of you will have come across the very short introduction series of short books published by Oxford University Press. He's written one on mathematics, which, as it happened, I read about 6 months ago, and it's a delightful overview and gives very good insight into the beauty of mathematics. I commend it highly. Now, of course, a lot of mathematics is done by individuals or small collaborations. Timothy's explored the opposite extreme. He asked on his blog whether it's possible to solve mathematical problems through massive collaboration. And he posed a particular problem as part of this so-called polymath project. And within about 7 weeks, he concluded that that particular problem was probably solved. Now, Timothy was recently knighted by the Queen for service to mathematics. And today he's going to talk about another of his interests, which is the challenge of automated theorem proving. So, Timothy.
Thank you very much. I'm very aware that there are likely to be several people in the room who are much more expert than I am in the field of automatic theorem proving. So I feel a bit nervous about the title here. I'm not really a sufficient authority to be able to give a proper answer to this question. So maybe a more accurate title would be, what are the prospects for the particular approach to automatic theorem proving that I myself like? And whether or not that's the right approach is a completely different question. So as a mathematician, I've always been interested in not just mathematics, but in how we come up with mathematics, how we find proofs and things like that. That's partly for a very practical reason. If you're going to spend your life doing mathematical research, then one of the things you want to do is make the process of doing it as efficient as possible, so you produce as much as possible or as good things as possible. And so just standing back and thinking, what am I doing when I'm doing it, I think is a good investment somehow. And so that's also with teaching. One of the jobs I've had in addition to research, is trying to help other people come to understand things that they don't understand. And again, I think one wants to think more abstractly about what it is to understand mathematics, what it is that the people you're teaching aren't able to do, that you want to get them to be able to do, how to get them to be able to do it, and things like that. And this all leads me into thinking very much about this general question of how to find proofs. And it's a short step from there to thinking about automatic theorem proving, because it's really the question, how do you teach humans to find proofs, is not that different, I would contend, although this is slightly controversial, from the question, how would you teach computers to find proofs? But I just want to sort of say a little bit more about what I mean when I say that I'm talking about one particular approach to automatic theorem proving rather than the whole field. So there are various spectra, I suppose one should say. So one is, let me just remind myself where, oh, here we go. Going from checking to proving. So sometimes when people use the phrase automatic theorem proving, what they're really talking about is the checking of proofs. They're talking about taking proofs, writing them in some formal language like Coq or something like that, so that a computer can check that it's valid. What I'm interested in is very much at the other end of the spectrum. It's improving. It's in sort of the ultimate would be you just type in a statement, your computer would spend a millisecond or two, and then up comes a proof of the statement on the screen. Of course, in general, that's not feasible. It's an NP-complete problem. So if you don't know what NP-complete means, it just means hopelessly difficult. But mathematicians aren't doing this problem in general. They're not taking arbitrary statements and trying to find proofs. They're taking very specifically sort of tailored statements that are sort of beautiful, interesting, important, relating to other statements, and that sort of thing. So that's really what I'm talking about. So I'm taking sort of natural, nice statements and trying to find natural, nice proofs. So another very important spectrum, just to sort of place what I'm talking about, is between machine-oriented and human-oriented. So roughly, the machine-oriented approach says, what is it that computers are really good at? They're good at searching through lots of stuff extremely fast. They have much bigger memories than we do. They've got a whole lot of brute power. What we're good at is a sort of ingenuity bit. So a sort of combination of our ingenuity and the sort of brute force of the computer should be able to do more than we can do on our own. So the idea there, roughly speaking, is to use the superior power of the computer and really exploit it in a way that would be impossible for humans. The human-oriented approach to theorem proving is to say, well, it really seems to be the case that humans are remarkably good at finding proofs, and they can find proofs of things that so far nobody knows how to get computers to find, at least on their own. So it makes sense if you're trying to program computers to look at how humans do it and try to imitate that. So there's a sort of balance to be struck. Do you use the brute power of the computer, or do you try to copy humans as much as possible? And I am right at what I'm interested in is right at the human-oriented thing. That's what sort of fits in with my interest in my own research and teaching and so on. And that is what I'm very interested in trying to get computers to do. I'll say what I mean, but I would classify myself as an extreme human-oriented whatever. I should mention at this stage that although it's probably best to regard this as a hobby in a sense, and the day job is my actual mathematical research. It's a bit more than just a hobby, and as I mentioned in my abstract, I've worked with somebody called Mohan Ganesalingam from the computer lab in Cambridge, although just saying from the computer lab is perhaps not doing him justice, because he's very, very good at mathematics, at linguistics, and computing, and all sorts of things. He's a very talented person indeed, with all sorts of relevant abilities. And I'll talk a little bit about our work at the very end, but because, as I say, I feel a bit of an amateur in a room full of professionals, I'll relegate that to the end, just to show you a tiny bit about what we've done. But really what I want to do more is just sort of, so to speak, play to my strengths and just concentrate more on the mathematical side. And one more spectrum between interactive and fully automatic. Do you want your program to be something that you keep giving it little hints to, which is an important thing, could be very useful, or do you want to be fully automatic? So what we're interested in is the fully automatic side, but actually that's not such an important distinction, because if you've got something that's fully automatic but can't do absolutely everything, then you've already got an interactive problem solver. Suppose you've got a problem solver that can do sort of moderately hard problems but not super hard problems. And if you're trying to solve a super hard problem, then you sort of chop it up into moderately hard problems, get the computer to do those, and everything could be much, much faster. So actually, a sort of a semi-powerful fully automatic prover would turn into a very useful interactive prover. Okay, so here is what I regard as the fundamental problem that I'm interested in. So this is where it's sort of I'm interested in, not just from the point of view of computing, but also from my own research, as I say, sort of what is it? How do humans find proofs as efficiently as they do? It's an NP-complete problem in general, and yet when we, for the actual problems that we come up with in practice, of course there are lots of open problems, but there's also remarkable success in solving some of these problems that look completely impossible to start with, and then eventually they get solved. I want to give a very, very simple example. It actually requires a tiny bit of group theory, but if you're not familiar with group theory, I think you'll sort of get the general idea, or get the general sort of broader point that I'm trying to make with this example. So one of the important facts about groups is something called the cancellation law. If ax equals ay, you have to prove that x equals y. This is true for ordinary numbers, but groups are a bit more sort of like a sort of abstract form of ordinary numbers. So here is a sort of what a human might do. Let's say, well, if ax equals ay, by one of the group axioms says you can find an inverse to A, which is sort of BA equals the identity. If you multiply both sides on the left by B, then you use the associative law. You can replace B times AX BA times X is the same as B times AX. BA is the identity. We've established that, so we get that EX equals BAX. E times X is X because that's the identity. So X is EX because you can swap things around when you have an equality. I'm just going through this rather fast. You do something similar on the right-hand side, and then you get a big chain of equalities, and you end up showing that X equals Y. That's sort of the steps, if you just go right back to the group axioms, that would need to be in a computer, and it's not very difficult for a human to come up with them. In practice, of course, a human wouldn't write out all these intermediate steps, and it would look more like this. You'd say, we've got that ax equals ay, multiply both sides on the left by the inverse of a, and then the inverse of a cancels with the a on both sides, and so you get that x equals y. Now, the slightly mysterious thing about this is it's a very, very simple proof for a human, but if you start thinking about how a computer might discover it, you get this rather odd thing that it's taken the original equation ax equals ay and made it look more complicated. Because if you just put an a to the minus 1 on both sides, you've got sort of a more complicated expression. And only after you've done that do you then get that a to the minus 1a cancels, and it gets down to something simpler. And if I go back to what we had here, sort of spelling out all the intermediate steps, then it really makes it quite a lot more complicated before you finally get to the simple x equals y. And if you've got something that's got to get more complicated first, then that makes it much more dangerous if you're trying to get a computer to search for the answer, because if you had an algorithm that just said, whenever you can spot a simplification, simplify, then you know that that's going to terminate. If the thing gets simpler and simpler, it can't go on getting simpler and simpler forever, so at some point it'll terminate. But if you're allowed to get more complicated, then there's all sorts of different ways that you could imagine getting more complicated. Perhaps we could have multiplied things on the right by a to the minus 1, or we could have taken the inverse of both sides, or all sorts of ridiculous things that we could have done. Why did we choose that one? If you just had a sort of brute force search, you'd end up looking through all sorts of different possibilities until you sort of stumbled on one that just happened to simplify when you got down to x equals y. And that would be very unlike the way a human works. So this is just why I give this example, to give a sort of, to say that even this rather simple problem for humans is quite subtle. If you're more of an advocate of the machine-oriented approach, then what you might do is, and in general with proofs, and this is a big difference between the way Mohan and I think about it and the way quite a lot of people think about it. So you can think of the search for a proof as a general sort of search problem. Computers can do quite a lot of search, but if you keep on sort of, you're searching for a step to do, and then each step you do leads to another search for a step that you want to do, and each step there leads to another search. If these searches build up, you get what's called a combinatorial explosion. Say there are two possibilities, and then for each possibility there are two more possibilities, and for each of those possibilities there are two more, then you're sort of doubling. And if you've got 100 steps to do, then you've got 2 to the 100 possible things to search, and that's just too big. So what people do is to say, well, if the search threatens to get too big, let's find clever ways of pruning it. You could imagine this with a chess-playing program. You don't want to look at every single possible position, so you have to find clever ways of ruling out some of the ones you don't want to look at. And it's a bit similar with looking for a mathematical proof. So the idea here is you would like to do a massive search, you can't, and so you sort of chop it down until it just becomes practical, then you use the brute force of the computer to do it. So that would be the sort of outside-in approach. And an inside-out approach would be the exact opposite. You basically don't want to, you want to start with the aim of using no search whatsoever. If a human would just say, of course you multiply both sides on the left by a to the minus 1, then so should a computer. And after a while you realize that even humans do a little bit of search, so you can't just rule it out completely, but you then just sort of build it up little by little. Just so instead of starting with a huge amount of search and pruning it, you start with a tiny little plant and sort of let it grow, so to speak. It's a different emphasis. But one of the difficulties that bedevils this approach is that it's very difficult not to come up with sort of ad hoc reasons for why you might say, well, in this example, we like to multiply on the left by a to the minus 1 for such and such a reason, but then that won't generalize to other problems. What one wants is some general principle that works here. And actually, unfortunately, I think the reason for this example is a slightly ad hoc one. I think the reason we find it obvious that we multiply on both sides by a to the minus 1 is that we're just used to ordinary numbers. With ordinary numbers, we just divide both sides by a. That's the cancellation law. And then we sort of know when we first start learning group theory that a to the minus 1 is sort of behaving like 1 over a, and it's our sort of analog of 1 over a. And so we just reason by analogy somehow and say, let's try and do something similar to what we'd do if it were ordinary numbers, and then multiplying on the left by a to the minus 1 is the nearest we can think of, and it works. But that is rather particular. Well, it's either rather particular to that example, or it requires you to understand all about numbers and how to reason by analogy and things like that. So that becomes a big task just for a very small problem. But I think that's possibly just the way it is. So why bother with the human-oriented approach at all? The machine-oriented approach has had some spectacular successes, one of which is a solution of something called the Robbins conjecture. I won't say too much about that except to say that it was an open problem of interest to mathematicians, and it was finally solved by a computer. So this was regarded as one of the great success stories of automatic theorem proving. The final proof that it found was fairly short, but the search for that proof was huge. So it had to sort of to run for a very long time, searching through all sorts of possible manipulations until finally it found one that got from the sort of starting point to the target, and then that proved the Robbins conjecture. But somehow that was a very special sort of problem, and not very like the questions that most mathematicians come up with most of the time, even undergraduates. For a lot of interesting problems, I'm not saying the Robbins conjecture wasn't an interesting problem, but for a lot of interesting problems, you get this problem which I've just talked about of combinatorial explosion. So you have the process of discovering a proof involves lots of steps. At each step, there are plenty of different things you could do. So if you did a brute force search, then the number of possibilities you'd have to explore would rapidly become completely impractical. So, and that's so characteristic of such a lot of mathematics that I just feel that the human-oriented approach is just absolutely essential. We're not going to get to a fully automatic theorem prover without taking very seriously how human mathematicians have evolved over the centuries to do mathematics. And another reason, actually, is that if you've got a process that finds a proof in the way that a human mathematician finds a proof, it gives you much more insight into that proof than if you just have a sequence of steps that happens to guarantee that the original statement is true. Guaranteeing that it's true is sort of worth doing in maths, but it's only a small part of the story. And what we really like out of our proofs is explanations. We like to understand why the thing is true. And one of the ways of understanding it is just to be left with the feeling when you read the proof that sort of with hindsight, maybe I could have found that proof myself. I sort of see where the ideas come from and that sort of thing. Actually, I mean, this is a criticism of some maths papers. Some maths papers are written in very cryptic ways. Okay, I can see that it works, but how on earth why formulate that lemma and so on? And that's very annoying, actually. But that people sort of write in a way that obscures ideas, but some people don't. And I think if we're having an automatic theorem prover, then one that can tell you its thought processes, and they're not, I searched a billion possibilities and this one happened to work, would give you much more insight. That would be very nice. So that's just another reason for being interested as a mathematician in the human-oriented approach. So I've said that there are some problems that humans find quite easy and computers still find quite difficult. I'm going to show you a couple of problems. And this is the first one. So the two problems I'm going to show you are consecutive problems on the first example sheet of a first-term undergraduate course in Cambridge. It's called Numbers and Sets, the course. So you don't set a question on an undergraduate example sheet. if you think it's going to be impossibly difficult. So, and this wasn't one of the, sometimes you do, you put it at the very end of the sheet and put a star. This was not a starred question. It was an ordinary question that it was expected that, you know, a substantial fraction of undergraduates would be able to do. Now, the reason this would be fairly hard for a computer, I think, and my guess is, or I'm not absolutely certain, but my guess is this is beyond current technology for a fully automatic theorem prover to be able to prove something like this. And the reason is that it's asking you to find something. It's asking you to find some n, some integer n, such that n plus 1, n plus 2, all the way up to n plus 99 are all prime numbers, and doesn't give you any clue about how to do it. So how might one try and do it? Well, the only obvious thing is just a brute force search. Does 1 work? No. Does 2 work? No. Does 3 work? But actually, it's a carefully chosen question. If you do a brute force search, you're going to have to go up to a very, very, very large n, and it's not going to work. So there are just too many primes. The primes do thin out eventually, but it takes a very, very long time for them to thin out. So brute force search is not going to work. But then what do you do? There's nothing in the question that sort of tells you what to do next somehow. So it's very hard to imagine how a machine would do it. Now, what I want to try to do is just break down a sort of typical thought process for solving this question. Not the only possible thought process, but just a typical one, into smaller units. And those smaller units, I think, should look much less challenging for a computer to do automatically. So I'm really just trying to convince you, I'm trying to explain, in a sense, why I'm really sort of have been convinced for a long time that something like this extreme human approach should be possible. Unfortunately, I can't claim that I have a program that's doing this sort of thing, but I feel that what's stopping me is simply that it's just a lot of work is needed to convert the sort of basic idea. I don't feel there's a fundamental obstacle. If I had a team of 20 people working with me for 5 years, all very much with the same sort of view about how things should be done, and we did nothing else for that, I think it would be possible to get there. What my experience with Mohan has been that we've got things to prove quite easy results, also sort of undergraduate results, but we keep finding sort of little tiny technical difficulties. They don't seem fundamental, but sort of, oh gosh, I hadn't quite thought about that. We have to sort of tweak, and it feels as if that process will converge, but it hasn't yet. Anyway, let's see how we might find. So first of all, let's just make the question just a tiny bit more formal. And it could be formalized much more if we wanted to make it comprehensible to a computer, but I'll use words like "we want" and things, but that's standing for an existential quantifier. And anyway, so we'd like to find an n such that n plus r is not prime for all r is 0, 1 up to 99. So that gives us our 100 consecutive non-primes. That's just saying what it means for it not to be prime. You need to have some a that goes into n plus r. I'm being a bit sloppy. I'm not saying that a mustn't be 1 or n plus r, and it must be a positive integer, but that's what I mean. It must be a proper factor of n plus r. So one of the standard techniques that one uses is generalizing. So when you see a number like 99, you think, well, that probably hasn't got a very fundamental role to play in this problem. Let's tidy things up a little bit, and we'll replace 99 by just some arbitrary number m. So then, one of the reasons for that is just not to get distracted by sort of irrelevant data, so to speak. But actually has another advantage, which is once you've made m a variable, you can try some other cases. And you can actually try simple special cases and not just sort of complicated ones. And a very obvious one, why not, let's just try m equals 1. So can we find an n such that both n and n plus 1 are non-primes, i.e. they've got factors? Now let's just consider, so we'd like to find an n and an a and a b. The a and b will be the factors, so we want a going into n and b going into n plus 1, and I'll just reproduce that up here. So what next? Well, if you're going to do something like that, a very standard, everything so far has been sort of standard proof-finding technique, so another very standard technique would be just let's pick the simplest possibility for A and see whether it works, see if we can get it to work. So we can find, so I'm just specializing at this point. I'm going to say instead of finding n, A, and B, I'm going to just declare that A is 2 and see whether it works. So we'll go for n and b, so 2 goes into n and b goes into n plus 1. Well, looks okay so far. We can certainly get 2 going into n, but let's just, we've still got this b to worry about. Well, let's try the simplest possibility again, the same technique. And, well, the absolute simplest thing we might try is 2, but if 2 goes into n, if n is even, n plus 1 will be odd, so 2 is ruled out. So let's try the next one. We'll try 3. So can we get 2 to go into n and 3 to go into n plus 1 for some specifically chosen n? And you're not allowed to choose n is 2 because the 2 wasn't allowed to equal n. So just make that clear. But if one thinks about it for a tiny bit, even with a brute force search, you quickly arrive at the result that 8 works. So 8 is even, and 9 is a multiple of 3. So 2 goes into 8, 3 goes into 9, and we've done it for that special case. So that seems to contradict what I've just said. So when I say are we done, what I really mean is, has that given us a sufficient insight to solve the whole problem? Does the fact that 2 goes into 8 and 3 goes into 9 show us how to find 100 consecutive non-primes? And the answer is no, it doesn't. It's just, unfortunately, it just looks like some experimental fact that doesn't have too much bearing on the general problem. So let's continue a little bit. Only thing I can think of at this point is just to try the next case. So let's try finding n, a, b, and c. A goes into n, b goes into n plus 1, c goes into n plus 2. And we dispose of this one fairly quickly because we take a is 2, b is 3, but once we know that n is even, we know that n plus 2 is even, and so actually we can just take c as 2. So that was not very important. I mean, it didn't really help us much. What about the next one? So what are we trying to do here, by the way? Why are we trying to do more cases? We're sort of hoping that at some point we'll stare at it and see some sort of pattern that we can then generalize. So n, a, b, c, d, a goes into n, b goes into n plus 1, and so on. So then we choose the simplest values. We've already know that 2, 3, and 2 are going to work for a, b, and c. And now we find, what could we do for d going into n plus 3? Well, because n is even, n plus 3 is odd, so 2 is not going to work. Because n plus 1 is a multiple of 3, n plus 3 is not a multiple of 3, so 3 doesn't work either. 4 doesn't work because 2 doesn't work, so 5 is the next possible thing that could work. So we think, okay, can we find an n so that n is even, n plus 1 is a multiple of 3, and n plus 3 is a multiple of 5? Now there's another question here, which is it worth the bother of trying to find such an n? In a way, it's not really, because when we found an n that worked for 2 and 3, when we found 8, it didn't really help. It just was, okay, it could be done, but it hadn't. The fact that it could be done didn't really give us a clue about how to generalize. So actually just experiment. We might want to do it to reassure ourselves, but it's not really going to help just to exhibit an n. So maybe we just don't bother. Instead, we just carry on with this pattern. So what happens next, let's just quickly, if you carry on this same sort of argument, n plus 4 is taken care of, and so we end up wanting 2 to go into n, 3 to go into n plus 1, 5 to go into n plus 3, and 7 to go into n plus 5, if we just carry on this general approach. And now, I think one can see a pattern. So what does 2, 3, 5, 7 suggest anything? Those are the first 4 prime numbers. And 2 goes into n, 3 goes into n plus 1, 5 goes into n plus 3, and 7 goes into n plus 5. Is there a pattern there? Yes, because 2 minus 2 is 0, 3 minus 2 is 1, 5 minus 2 is 3, and 7 minus 2 is 5. So it seems as though what we're getting all the time is that we want primes to go into n plus that prime minus 2. And we would want things to work up to n plus m, so if you look at it a little bit, you find that we would like this condition to hold for every prime up to m plus 2. It's just, if you're not following exactly what I'm saying, I think I just want to go a little bit, I want to whiz through a little bit. But just believe me that was very easy, what I did. If one thinks about it, there's a little bit of time to think about it. And it's reasonably easy to show that if you've got that condition, and I'll jump over that part, then you will in fact be done. So if it is the case that for all primes up to n plus 2, p goes into n plus p minus 2, then you'll have your m consecutive non-primes. So that's the general principle. We want p to go into n plus p minus 2 for every prime up to n plus 2. And now we realize that we can simplify it. So p going into n plus p minus 2 is the same as p going into n minus 2. If n plus p minus 2 is a multiple of p, then so is n minus 2, and conversely. But it just looks nicer not to have the p here. So we now want n minus 2 to be a multiple of every prime up to n plus 2. And at this point, it's become a very easy problem. But let's just spell it out. Can we find a positive integer that's divisible by all primes up to n plus 2, which would be our n minus 2? Yes, just multiply all those primes together, and then of course it's divisible by all those primes. And actually that's finished. We found a solution. So what is the solution? It's multiply the first few primes together. In the case of 100, multiply all the primes up to 101 together, and subtract 2, no, add 2, and that will be your starting number, and then the next 100, or that number and the next 99 will none of them be prime. So there's a whole process. I've sort of broken down the thought process into much smaller steps. If you go to a supervision and you have a bad supervisor, the supervisor will say, consider n factorial plus 2, 3, let's take 101 factorial. Then 101 factorial plus 2 is a multiple of 2, 101 factorial plus 3 is a multiple of 3, all the way up to 101 factorial plus 101 is a multiple of 101. So it was easy. And of course, it's very easy to follow that argument, or if you don't follow it, if you're an undergraduate mathematician, it's very easy to follow that argument, but absolutely no insight has been given into how to find the argument. Right. And that's the sort of thing for a computer, just sort of happening to think of 101 factorial plus 2, 3, 4, 5 is not feasible. So this was the next question on the same sheet. So here we have a sequence which we get each term, we add 2, then we add 4, then we add 6, and then we add 8, and so on and so forth. And the question is, do you always get a prime? So how might one go about that? Well, here's a case actually where it turns out that if you use brute force on a computer, you can solve it in very short time. But you'll get an extremely unenlightening solution. It'll just sort of, here's one that's not prime. And it would be just a bit too tedious a brute force for a human to do. For a human, it's much better to think. So the obvious thing to try first is to look at the next few terms of the sequence. So 61, we add 10, add 12, add 14, add 16, add 18, add 20, and all those numbers are prime. So after a while, when you do that, you start losing heart and thinking, well, perhaps they are all prime, or at least I'm not likely to find a composite one for quite a long time, and so maybe we should sort of step back and see whether there's anything else to do. Well, this is going to take much less time than the previous one. There's a pretty obvious first thing to do, which is to find a formula for the general term of this sequence. And what is the nth term? Well, it's 41 plus 2 plus 4 plus 6 plus 8, all the way up to, as it turns out, twice n minus 1. And a human would do this by, maybe a computer would do that by just sticking it in Mathematica or something like that, I don't know. But a human might do it a bit like this. You say, well, this is the sum of the first lot of even numbers, but I know what the sum of the first n whole numbers is because I was at school. I did A-level, and it's nn plus 1 over 2. So if you double that, I'll get nn plus 1. But if instead I only go up to n minus 1, I substitute n minus 1 for n here and get 41 plus n times n minus 1. And so that's a formula for the general term. Not too important how you come by that. It's the sort of standard thing to do. So now the problem is, are all numbers of this form prime? So either you see that straight away, in which case it's a mysterious thing, and I don't like mystery in mathematics. So let's just see what one might do if you didn't see it straight away, and maybe you don't. So we sort of say, could it ever be an even number, for example? So we'll try 2 being a factor. So could this ever be even? The answer is no, because one of those 2 numbers will be even. So that product will be even, and then when you add 41, it'll make it odd. And a similar argument shows that it can't be a multiple of 3. There's slightly more cases to check, but it turns out this can never be a multiple of 3. And in fact, if you want, you can check that it will never be a multiple of 5. But after a while, you'll start getting a little tired of this case checking. Now, when you get tired of the case checking, then instead of just trying any old small things, instead of trying the simplest thing, you might say, there is another problem-solving technique, which instead of just looking at the smallest thing or something like that, try and find something that's actually connected with the problem. So are there any integers that are connected with the expression 41 plus n times n minus 1? Well, of course, there's one staring us in the face. It's 41. So it might be rather natural. I mean, perhaps it would turn out that in reality we wanted to look at 40 or 42 or something, but 41 looks like a pretty good candidate for something to try. So can we find an n for which 41 goes into 41 plus n times n minus 1? That is very easy, but let me spell that out by dividing up into even smaller steps. So what does it mean for 41 to go into n minus 1? It means that we want an n and an m such that 41 times m equals n times n minus 1. And now we can just solve it by matching up the 41 with the n and the m with the n minus 1. Just say, well, let's take n to be 41, n minus 1 to be m, which means that m is n plus 1, so m is 40. And then we're done. So going back to here, if n is 41, then this is a multiple of 41, and so it's not a prime. And there again, you could just say that straight away, but there is a sort of genuine problem-solving technique. Okay, so of course it's not enough to show you that the search for a proof can be broken up into small, simple steps in the way that I've tried to do. By the way, there's a very important distinction between the proof being divided up into small, simple steps and the discovery of the proof being divided into small, simple steps. I'm talking about the second rather than the first. So the small, simple steps are things like, let's generalize this, or let's look at a simple special case, and that sort of thing. They're not, this implies this, implies this, implies this. That's a completely different thing. It is a very interesting fact about mathematics that proofs themselves can be divided up into tiny steps. But that's not the fact that concerns me right now. So we've got all these devices. It's not enough to show that a sequence of those devices will end up in the discovery of a proof. I've also got to give you some account of how you choose the particular devices and you don't choose other ones that are totally unsuitable. So there are all sorts of other things that one could do that wouldn't have helped to solve those problems. And so how did I know to go for the ones that would? So that's one problem. And another problem is a sort of lower level problem somehow. Once you've actually chosen which problem-solving device to use, like generalize or something, how do you actually go ahead and do it? I think the second is much easier than the first to automate, so I'm going to concentrate on the first. So that itself divides up into 2 sub-problems. So one of the things you want to do when you're looking for a device is make some estimate of how much effort it's going to be and how helpful it's likely to be and that sort of thing. So how do you actually do that? How do you look at it and say, oh, generalizing looks as though it's going to be good here. Trying setting n equals 1, that's not going to be any help at all. So a human, we make these judgments quite easily, but how would that be an automatable thing? So that's one question. And another question is, supposing you can do that, so supposing you can make good judgments about how useful various techniques are likely to be. You won't be able to say with absolute certainty that this technique is going to help and that one's not going to be very helpful. It'll always be some probabilistic judgment, which you'll then have to go and actually do it and see whether it does help. If you didn't have to do that, you'd have solved the problem already, so to speak. So if you've got assessments of various different things to do, how do you actually go ahead and decide which one to do? What would be a good strategy? So I want to discuss this second sub-problem, the sort of strategic problem that you face when you're doing maths. So it's actually a special case of a much more general problem. So you're sort of in some environment, and the environment I'm thinking of here is It's you and the piece of paper on which you've scribbled and the problem that you're trying to solve and the thoughts that you've had. And you have a choice of actions that you can make. And these actions you have sort of some information about what you think the rewards of various actions will be and what the costs of various actions will be. So a typical cost will be just the time it takes or the annoying effort it takes to do some calculation that you know that you could do in principle, but it might be rather tedious. And then the sort of possible rewards are, maybe if I do that, that'll give me some insight which will help me later on to solve the problem. So you've got these sort of costs and rewards and a goal that you want to get to, which is solving the problem. But it's a much more general thing, which is this idea of actions and costs. So for example, there's things that people look at, which I'm sure many people know about, called Markov decision processes. This sounds quite like Markov decision processes. Although a fairly important distinction between this and Markov decision processes is that we don't at all have perfect information about what's going to happen later on if we take various actions. So if you do know about those, there's also a very strong sort of information constraint. Although people have thought about that sort of thing as well, about acting when you don't have perfect information. So the point I want to emphasize is that this sort of question has been studied quite a lot. So I think it's worth studying it in the context of mathematics, although I think it raises interesting difficulties that are peculiar to mathematics. There's something a bit odd about using a probabilistic model for something that's as deterministic as mathematics. So you might sort of say, I'm going to do a calculation, and I think the probability that it will all simplify down to something nice is quite high. If you say, what does that mean? Either God sitting up there either knows that it's definitely going to simplify, or that it's definitely not going to simplify down to something nice. So what do you mean? And that's actually, I find that quite an amusing problem, but it's not something that puts me off, because we're all Bayesians these days, and sort of probability is not a sort of measure of what will happen if you repeat the experiment over and over again. It's a sort of measure of our uncertainty and that sort of thing. So I think that's a probabilistic model is appropriate even in this rather deterministic context. Without a complete solution to this problem, let's just distill a couple of general principles. So something is good to do if it's cheap, and something is good if there's a reasonable chance that it'll be helpful. So if you've got a very complicated calculation, you perhaps try and do simpler things first. Or if you've got a simple calculation, but you're pretty convinced it's just going to be completely irrelevant, like that one of seeing whether 5 went into 41 plus nn minus 1, it would be fairly simple, but unlikely to be helpful, so you just don't bother with it. Or you don't bother with it if you're trying to optimize your efficiency. But yeah, sometimes you find that there are some easy things you can do that are probably not going to be all that helpful, and some things that look as though they might be quite helpful, but it's going to require an awful lot of thought to make them work. Which do you do first? And there's a balance. So let's just have a look in this, going back to this example, about how we might choose a problem-solving device. So remember, we wanted to find an A and an N such that A goes into 41 plus nn minus 1. So here's a selection of problem-solving devices that we might have tried. So one was have a look at the smallest value of n that isn't yet ruled out and then go for A, but we did that right at the beginning. We looked at some small values of n and we found that all the numbers were all prime. And so we sort of know now that that doesn't work. It's not a ridiculous thing to try, but we've now established that it won't work. Another one might be find the smallest value of, well, actually, yes, I'll come to the assessments of this on another slide. But so another one would be find the smallest value of A and then the smallest value of n, or find the smallest value of A that hasn't been ruled out and then see what that would tell you about n, and then try choosing an n that's related to the problem, try choosing an A that's related to the problem, or try generalizing the problem by changing 41 into m. And some of these are good, and some of these are not so good. So let's have a look at some not so good ones. So I've just said this. So if you try the smallest value of n that hasn't been ruled out, you find that you look at these numbers, 41, 43, 47, 53, 61, 71, 83, 97, must stop. And they're all prime, so we don't really get anywhere. The next one was to try finding the smallest value of A and then the smallest value of n, but we sort of already know that small values of n aren't going to work, so this strategy doesn't, you can sort of tell actually that it won't be helpful. What about the smallest value of A that hasn't been ruled out, and then look at the constraints on n? So you might say, let's try A equals 2. I talked about this before. So that's saying, can you find an n such that 41 plus n times n minus 1 is even? And it turns out you can't. It's always odd. So you might say, well, let's try a equals 3. Can you find one that it's a multiple of 3? No, it turns out it's never a multiple of 3. It's never a multiple of 5. And when you've tried a few of those, this is a point I want to emphasize, it was sensible to try out small values of a to start with, because it's a simple thing to do, simple thing to see whether it works. But after a short while, first of all, the larger a gets, the harder it gets to see what happens. And secondly, the larger it gets, the more you sort of increase a and don't get anywhere, the more you start to feel this whole approach isn't getting anywhere. And so your sort of assessments of the probability of that trying small values of a is the way to go changes, and you start to sort of balance between rewards and ease of calculation changes. So we get new information that suggests that maybe this approach is not a good one. So it wasn't hopeless, but it turns out not to be good. So we want to try something else. And then all three of these, it turns out, are good ones. So if you choose an n, you could take n is 41, problem solved. If you choose an a is 41. That's one I actually used before, problem solved. 41 divides n minus 1, then okay, n is 41 will do fine. The third one's slightly subtler. If you generalize, rather as we did with the first problem, by replacing 41 by an arbitrary integer m, that immediately sort of tells you not to look at small things like 2 and 3, because you don't know anything about m. So then you're forced to think of something that's somehow related to the problem, or built out of m in some way, and it just forces you back. This idea of generalizing forces you back to these strategies that were good ones, and away from the strategies that were bad ones. So it's a sort of good in a more meta sense. Don't take this slide too seriously, because I'm not an expert on machine learning. So this is just my little hunch. I'm in a room full of people who will probably have exactly the opposite hunch with much better reason than I have for having the hunch, but let me just say. So I feel that there could be a role for machine learning in mathematics, but a rather restricted role. So I think machine learning might be good for those situations where, but I would maintain these are very rare, these situations, where humans can do something with ease, but when you ask them how they do it, they just cannot tell you. So if you ask me, how is it that I recognize my mother's face or something like that, I can't really explain it. I certainly can't explain it in such a way that if you met her in the street, you'd say, wow, that must be... but I think that sort of situation doesn't occur very much in mathematics. My experience seems to be that even if you think you've had some sort of idea that just popped into your head out of nowhere, actually, if you are not lazy and you think about it hard, you can work out at least a plausible story about how it might have popped into your head or how it could pop into other people's heads. And so I feel that sort of saying, let's try machine learning, feels to me like a sort of cop-out, although that's not to say that I wouldn't be absolutely fascinated if somebody managed to do something using machine learning in a serious way that could sort of come up with ideas. But even then, I'd be a little bit disappointed, because then this idea of explaining thought processes might be rather hard to get. It'd be more like, you put it in your neural network, sort of outputs the something that sort of tells you what the idea is, and it just looks a bit like magic, because it's rather hard to sort of open up a neural network and understand how it's working. Maybe not always completely impossible, but I feel on unsafe territory here, so let me pass quickly on to discuss very briefly at the end what I've done with Mohan Ganesalingam. So I've been talking about the high-end problems, sort of how we choose strategies and things like that, but there's a sort of lower-end problem. So if you want a machine to think like a human and avoid search where humans would avoid search, then there's quite a lot to be said for looking at problems that humans can solve doing no search at all. There's a whole class of problems that we would class as routine. I think of them as problems or proofs that I don't have to, all I have to do if I'm giving a lecture where I have to present such a proof is just remember the mnemonic, do the obvious thing at each stage, and you'll get there, and don't worry, nothing will go wrong. So I call those routine proofs, ones that you can find just by doing the obvious thing at each stage. And they definitely exist as a sort of human phenomenon. And so if you're trying to find something that doesn't do search where humans won't do search, then you have this sort of general idea that you'd like to find an algorithm that when humans don't search and backtrack and that sort of thing, the algorithm won't. If a human just goes straight from the hypotheses to the conclusion, so should the algorithm. So that was a challenge we set ourselves within one small subdomain of mathematics, which was abstract analysis, metric spaces in particular. So this is, in a way, I think the most striking thing to other people about the program, but it wasn't our main focus, is that we could quite easily get it to output its proofs in pretty much natural language. So I'll show you what a proof looks like. We actually did a test. I won't do it here, but we did a test of on my blog. I posted output from the program and some human-written proofs and asked if people could tell the difference. And more people voted for our thing than for the human ones, but it was not a sort of overwhelming majority. It was 40% got it right and 60% got it wrong or something like that. So that was a sort of mini Turing test, so to speak, that our program passed. So here was the problem. If you haven't done second-year undergraduate mathematics, then this won't make too much sense. But at least I think you can sort of look at that and see that it looks sort of vaguely like the kind of prose that you see in a... It's sort of not 100% formal language. It's got all these sort of words in and... I might say just a tiny bit about how that... So one of the key things we wanted was... So one thing you might do for this would be first you find a proof, and then you do a whole lot more processing in order to turn it into a natural language output. We very much didn't want to do that. We wanted to have something that reflected the thought processes of the program. So it was important that it should be a sort of local method of producing the output. In other words, it would have a thought, it writes down that thought, then it has another thought, it writes down that thought, it has another thought. So what you see here is basically what's going on inside the program. It's not some cheat where you reconstruct a sort of human readable proof after concealing all sorts of search that the program did. There's a tiny bit of sort of, not exactly cheating, but sort of tidying up. So if you just do it sentence by sentence, then you find that you get sort of ugly little repetitions from one sentence to another, and where a human would sort of, we've established that we're talking about this, and so we can use a pronoun here instead of, or whatever it might be. So a few tiny little adjustments, but really not very much at all. This was not a... So Mohan actually works on something much more difficult, which is understanding the sort of text that you'd read in a mathematical textbook and converting it into sort of more logical form. This is the reverse process. You have something in a logical form and you just want to produce some text that is more human-like. That's much easier because you get to choose what your text is. If you want to do it the other way, you have to resolve all sorts of ambiguities. That was the main challenge for him, and that's very much harder. But nevertheless, his expertise was extremely useful. Well, his multiple expertise was extremely useful for all these things, but it was particularly useful at this part here. And I think I will stop there.
Well, thank you, Timothy, for a very, very thought-provoking talk. We have a little bit of time for questions. I might take the liberty actually of asking the first question, if I may. You said there that we're all Bayesians, so music to my ears, of course. My work is done. If mathematicians are to be Bayesians, should they not therefore move beyond saying that a theorem has been proven or not proven and talk quantitatively about the probability of it having been proven? For example, if a computer has just checked the first billion cases and not found an exception, then a rational betting mathematician would presumably change the bet that they would make based on the evidence provided by those first billion cases, even though, of course, it doesn't constitute a proof. Any thoughts?
Yeah, well, one thought is that you have to formulate what you're talking about rather carefully. So, for example, if I say theorem, every positive number is less than 10 to the 100, and then you sort of check the first billion number, then it's a rather interesting question, actually. when it is that looking at a whole lot of cases constitutes evidence for something, and when it's not. So a case where it is very compelling evidence is Goldbach's conjecture. So that says that every even number is a sum of, or every even number beyond from 6 onwards is a sum of 2 prime numbers. And if you use various heuristics about the primes being sort of reasonably random, you can actually predict it's not just that every even number ought to be the sum of 2 primes, but it ought to be the sum of 2 primes in several ways, and moreover you can estimate roughly how many ways any given large even number ought to be expressible as a sum of 2 primes. And if you compare that against a graph of how many ways these even numbers actually can be written as a sum of 2 primes, the agreement is quite astonishing. So when you see that, that becomes very compelling evidence that the heuristic about the primes behaving in a random sort of way is correct. And I think there'd be a lot of controversy if you then tried to sort of convert that into a number, because somehow those numbers, they don't seem very robust. You know, if somebody then suddenly proves an unexpected fact about the primes, then maybe your whole estimates would change. But perhaps that's actually what should happen in a Bayesian world. Some new piece of evidence comes to light, and then your estimates of probabilities change. So it feels to me as though there are possibilities there, and there are also obstacles to making those possibilities work.
Oh my goodness. Yes.
So you say that you want to avoid backtracking in a proof like this, but you haven't mentioned sort of human experience. You know, an A-level student might do a lot of backtracking to solve a problem, and then when he's got his undergraduate degree, can see the answer straight away. So can you make the computer sort of learn from past successes in the same way that human mathematicians do?
Well, I regard that as one of the major challenges, basically. So one which I don't have a clear idea how to do. I mean, it is a rather mysterious process when you watch human mathematicians learning, say, an undergraduate course. If you set them some well-chosen exercises, they sort of do those exercises, and then something clicks, they've got the idea, and in future they find that sort of thing easy, even if they found it hard before. Because something's going on that once they've sort of done a certain sort of struggle, after that it's easy. But what has happened for that to happen? I don't know. So that is sort of the problem of, how could you get a program to learn from experience? So I think at the moment, I think to try and tackle that would be setting our sights very high, indeed. So at the moment, I think our focus is more on, can you just make a program that could be taught? So you sort of, let's say a program that, as long as you can say, so you have to tell it the abstract idea that lies behind a particular class of problems, let's say, rather than, it is a question I find very fascinating. But also, another thing is I would like to make clear that what you said before, one of the other things you said is very important, that different people with different experiences will backtrack by different amounts. So everything is always sort of relative to the experience of the person, and the same would be true if you're serious about imitating humans, would be true about programs. So what I would want is for a program, maybe I should sort of make it slightly more precise. So a program should not backtrack if a human with a comparable level of experience to what you've given the program would not backtrack, something like that. In order to get to sort of the singularity, I think you'd need programs that can learn from themselves, maybe even set their own exercises, and once they can do that, then you just stand back and wait for the theorems to come rolling out.
I think the thing that's going to make difficulties for you is common sense, which basically can be defined as the accumulation of a vast amount of trivial knowledge. So for your first example, certainly and I imagine many people who know some mathematics will say, of course, the answer is no, I forget how you put it, because by the prime number theorem, and even if they don't know the prime number theorem, they know the primes thin out, therefore it's impossible that 1% of numbers are going to be prime forever. So they will know the right answer immediately, simply because of their background knowledge. And in fact, to me, the idea of multiplying a bunch of numbers together also occurred immediately. And that, I assume, comes from the insight I have. I do have a maths degree, but I've only done maths long ago. And your second question, that was even easier. To my mind, the immediate thing said was, the prime numbers don't behave like that. And this is a knowledge that any mathematician is just going to, I assume you agree with me, and everyone just knows. They just don't behave, you don't have these simple things that say, oh yeah, all of those are going to be prime. And this is the combination, as I said, of reading lots and lots of mathematics books and somehow accumulating vast amounts of knowledge. But this is known to be a very difficult problem in AI. You make these vast encyclopedias like Psych, in which I type in mountains of trivial facts and then try and get natural behavior out of it. So, I mean, this is what you're up against.
Yes, although the point I was sort of making was that with those examples was I agree that for a really experienced mathematician, the solutions would sort of pop into your head. But it is also possible to solve them if the idea doesn't pop into your head, if you've got much less experience. And so, there's, you know, for a first-year undergraduate, they wouldn't know the prime number theorem, so they wouldn't necessarily think, oh, the prime's going to thin out enough, so it's obviously going to be true. Actually, another sort of small thing is I think the question is find an n that works rather than just show that there exists an n. So that would mean that appealing to the prime number theorem would not be enough, because it would just be a sort of abstract existence proof. But that's a sort of pedantic point. So I think that may, I think this sort of accumulation of common sense, I'm sure it would be a challenge, but I don't think it might be enough of a challenge that it means that there are significant limits to where one can go with this sort of approach. But I think what I've tried to convince you of is that at least one can get started. It's possible to solve these problems or to break up a thought process into small ones, even if that thought process is not something that an experienced mathematician would do, but it could be something that an inexperienced mathematician might do to get from sort of zero to solving those problems. So it's not obviously correct, this, but I have a sort of hope stroke belief that mathematics is a sort of domain where where some of these notorious AI problems can somehow be sort of sidestepped. But I admit that could be wrong, and could eventually find that we just get stuck because of very notorious problems.
So there are quite a lot of people still wanting to ask questions, but I think in the interest of time, perhaps we'll bring the formal questions to a conclusion. Sir Timothy will be staying around for a little while. You're very welcome to ask him questions informally outside. Please do join us for drinks afterwards. But first, please join me in thanking Sir Timothy for a fascinating and delightfully presented lecture.